Lesson 3 on waves, and this is the theory of two-slit interference, and it is for year 13 physics. So what I have drawn over here is two slits, and the distance between the two slits is d, and this is your central antinodal line where n equals 0, and this is the next antinodal line. Okay, and in order to form this point here, waves from this slit as well as waves from the other slit have to meet to form that first order number or that first antinodal point there. Now if you look at this big green triangle over here, this length is almost the same as that length. So in other words, we say sine theta is almost equal to tan theta, and this is okay for small angles that are less than 10 degrees. Okay, and so that's equal to x divided by L. Okay, now look at the small triangle over here. Okay, and in this small triangle, here's your theta. Your theta is here. Now what is this? This is the path difference. This is the extra length that the wave from this source has to travel compared to the wave from the other source. So this extra little bit is your path difference. That's this one over here. And if I drop a perpendicular down, this is your angle theta. Okay, so over here, sine theta is opposite over hypotenuse, so it's PD. The opposite is PD, and your hypotenuse is D. Now, sine theta, we know that path difference is n lambda. Okay, so in place of path difference, you put n lambda over D. So if you rearrange it, you get n lambda is d sine theta. So the formula for any antinodal line is n lambda is d sine theta. But if you use sine theta is x over L, then you can get n lambda is dx over L. Okay, and this formula can only be used for two slit interference, not for anything else. Where the angles are where the angle is very small and the fringes are all quite close together. Okay, for any nodal line, so these are the dark spots or the quiet spots or flat spots if it's water, because the path difference is n minus half lambda is d sine theta, or n minus half lambda equals dx over L. Okay, so what is this x? X is the difference between two consecutive bright spots or between two consecutive dark spots. Okay, that's x. And the central antinodal line is n0, and you've got the other ones as 1 and 2 and so on. Okay, now coming on to some explanation questions using this n lambda is dx over L or n lambda is d sine theta. So just a couple of questions. What happens to the fringe spacing if a longer wavelength is used? So go with this to start your explanation and then move on to that. So since n lambda is d sine theta, when wavelength increases, sine theta is going to increase. So if sine theta increases, theta will increase. So the fringes are going to be further apart, or your path difference is going to increase. So the other thing you could add is that path difference, because that is your n lambda, increases. So that's quite a good thing to add on to this. Okay, for you to get all your marks in an exam. So here's the difference. So if I have green light, which has got a smaller wavelength compared to red light, green light, the fringes are closer together as opposed to red light. So this angle theta for the red is bigger than this angle theta for the other one, because your path difference is n lambda. So if lambda increases, your path difference increases. Then what happens to the fringe spacing if the slit spacing, that is D, increases, that means if you're looking at two slits, one of them the slits are far apart, the other one it's closer. So how do you explain this? Again, go with n lambda is D sine theta. When slit spacing increases, your D is going to increase. So what's going to happen? Your n lambda is the same. So if D increases, then your sine theta has to decrease. So theta will decrease, hence the fringes will be closer together. Okay, so here's your answer for that one.